Okay, so at this point we're ready to state the very interesting theorem, which I was very excited to talk about this morning, and I'm still very excited to talk about this afternoon. So what does this theorem say? It's essentially stating the equivalency between regular expression and FAs and, in general, regular languages. So given some alphabet sigma, the family of languages described by regular expressions, which we denote L sub rex, is the family, so it's a set of sets, it's a set of languages, L of R, where R is a valid regular expression over sigma. And so, of course, you see why we needed to define formally what a valid regular expression was, because now we can formally talk about L sub rex. And so the theorem states that this family of languages is exactly equal to the family of regular languages. And so what the immediate implication of this is that now to prove that a language is regular, you have many options, right? The first option that we saw in lecture 3 was you can create a DFA that accepts that language. Then in lectures 4 and 5, we saw that you could also create NFA and NFA with epsilon transitions. Then in lecture 6, we showed that you can also use closure properties. And now today, we can also use, it turns out, regular expressions to prove that a language is regular. How do you do that? You just create a regular expression that describes that language. And then, of course, formally speaking, or rigorously speaking, you need to prove the correctness of that regular expression. We're not going to do that here because it's tedious and it's not all that interesting. But in case you're interested, usually when you want to prove the correctness of a regular expression, you, of course, want to show something that looks like the language described by some regular expression is equal to your language. And so what you say is you say pick some string that matches, that you know matches the regular expression R, and show that that string must satisfy the definition of L. And then again, pick some string X, which belongs to L, and so it satisfies the definition of L, and show that there's always a way to match it with a regular expression R. And so in that way, you can kind of see that there's kind of this proof of existence that you sort of implicitly need to make. And so in that way, that's why these proof of correctness are similar to the ones of NFA. Because in NFAs, you have to show the existence of a path that goes from some start state to some accept state. In this case, instead of the existence of a path, it's the existence of a pattern match. Now, what is an immediate implication to this implication? Well, it's that if we're given some alphabet sigma, let's use the pointer. If we're given some alphabet sigma, and we have a finite language defined over sigma, so for instance, that language is composed of n number of strings, where each of these strings, ai, are in sigma star, then this finite language will be regular. Okay, why? Because I can create a regular expression that describes it, and that regular expression is super compact, super easy to write down. It's going to be a1, or a2, or a3, or and so on, an. Right? This clearly describes this language L. Why? Because take any string W in this language, it's clearly going to match one of these patterns. Then take a string that matches one of these patterns. It's either going to be this one, this one, this one, or this one. And so clearly that string is also in this language. Okay. But in your assignment, I don't want you to prove this using regular expressions. So in assignment 2, I ask for you to give an explicit construction of an FA or an F, or, well, in particular, an NFA or an NFA with epsilon transitions, and to prove the correctness. Okay, good. So this is an awesome, very useful theorem, but now we actually need to prove it. And so because it's a theorem that essentially states the equality of two sets, what we're going to do is we're going to do a double subset inclusion proof. So we're going to show that L sub rex is exactly L sub reg. And so to do that, we need to show that one is a subset of the other, and the other is a subset of the one. Okay. So this first direction is showing that L sub rex is a subset of L sub reg. So in other words, if you have a regular expression R, then it describes a regular language. Well, how do we do that? Fortunately, it's a very easy proof. It's a very easy proof because what you do is you first show that the languages denoted or described by the atomic regular expressions are regular. So you do that first. And then the second part of the proof is you say, well, I know that the language described by any other regular expression can be joined together using the language operators, the union, the star, and the concat, because those are exactly the language operators that map from the regular expression operators that allow you to create other valid regular expressions. And so then we can use the closure properties because we know that regular languages are closed under the union, the concatenation, and the star. We can then show that this immediately implies that any other regular expression that's built up from these atomic regular expressions using the regular expression operators that we saw must be regular. Okay, so that's the whole idea of the proof. I think I'll just breeze through the details. So here I list out what the atomic regular expressions are. Then I list out what the languages described by each one of them are. And then I create an FA which accepts each of these languages. So in this case, I have NFAs. This is an NFA that accepts the empty set. This is an NFA that accepts the language containing the empty string. And this is an NFA that accepts the language containing the string A. Okay. And then, like I just said, the language denoted by any other regular expression can be found by taking the union, the concatenation, or the star of the languages denoted by the atomic regular expressions. Why? Because take any other valid regular expression, it's combined together using the regular expression operators, which I presented before, so the plus, the dot, and the star. And these exactly map to the union, the concat, and the star for languages. Okay? But by the closure properties, these languages will also be regular. And amazingly, that completes the proof of that direction. I guess I shouldn't put a box there because I'm not quite done, but the fact that this proof is so simple and so nice makes me very happy. Okay. I think I'll stop the video here and do the other direction in another one.